All right, good evening, College Trig, 8.6, Vectors in Space. We live in a 3D world. Let's start talking about 3D things. Um, the nice thing about today is it's very similar to working in 2-space. We just have another parameter to consider. If you've never worked with 3-space before, it's nice to notice how we look at graphing things. Notice our new parameter is k in vector form, but it is z as a coordinate. When you typically graph, when I usually draw a graph of this, I draw just the positive coordinates, and we'll talk about how this is a right-hand system here. But these are representing the positive directions. So this is positive x, this is positive y, and this is positive z in three-dimensional space when we typically graph it like this. I have this nice applet here on Geometry Sketchpad that you can kind of see. So this is our normal XY plane. If we go ahead and drop the y-axis flat, okay, it's going to look like this. And now you can see it's similar to our XY axis here. So this is slightly different because our y-axis is vertical and our x is y, but you'll get the idea of trying to help visualize this. So we're going to plot the point x being 6, y being -4, and z being 3.5. So if we plot these points, we can see it's going to take our x out to 6. It's going to take our y, -4, so it's going backwards. And then we see our z is going to be the vertical, and it's going to plot out there. So we can see our point that would be 6, -4, 3.5 could be graphed like that. So this is just to kind of help us visualize three-dimensional space here as we start graphing and thinking about vectors. So nice thing about these, our formulas are very similar to two-dimensional space. Notice we just have a added parameter of z here. So for the distance formula before, we just had this piece dealing with third-dimensional space. We add our z component, and again, it's just the differences of those x's, y's, and z's squared. Sum them up and take the square root, and we can find the distance or the magnitude. So this could also be our magnitude of some vector u being the actual distance that is. So a position vector, similar to how we had it for our just 2 dimensions, we take the differences, doing x2 minus x1, that's our I parameter, y2 minus y1 is our j. We're just now including our third parameter of z. Okay. A visualization here as we're thinking about this is here. Just remember our position vector, no matter what points we have in space, this is the vector connecting our two points, P1 and P2, but as we rewrite the position vector, it is reset back to the origin with the starting point there. So keep that in mind, very similar to our two-dimensional vectors here. So let's look at this example here. So if we want to first find the distance between the 2 points, we're going to be that d is the square root and keep that long. So I'm just going to do, if this is P2, P1, this is going to be corresponding to my second point, x2, y2, z2, and x1, y1, z1. So I got to keep that order consistent throughout. So I'm going to do -1 minus 2 squared plus 3 minus 3 squared plus -2 minus 0 squared. So I get the square root of -3 squared. The y parameter drops out, plus -2 squared. And then I get the square root of 9 plus 4, which is equal to the square root of 13. So that is my distance between P1 and P2. The position vector, again, what's nice about this is we've already done a lot of this math. If we did this math and kept this according to x2 minus x1, x2 minus x1, this is now just going to be my position vector. So my position vector here is going to be coming from here, being my x parameter. That was negative 3i. I have a plus 0 j parameter, and then I have a negative 2 k parameter. So if I stay well organized, I don't need to double up my work here in finding my position and distance as well. All right, so you can see this is how the book worked it out with that. So these formulas, make sure you're at least aware of. It's just pretty much saying it's very nice because it's very similar to our two-dimensional. If we were wanting to add vectors, notice that A's are grouped, the B's are grouped, and the C's are grouped there. And that's consistent throughout there for adding and subtracting in here. So you can see the subtractions very much the same. If we're multiplying by an alpha, a constant, a scalar factor, notice that's just multiplying your A, B, and C by each of them, and you get your new vector. And then the magnitude, again, is just the squares of the I component, J component, and the K component. So really nice parallels to our two-dimensional plane can be drawn. So what I want you guys to do is, how do you think about these questions? Pause it for a second, and we'll go ahead and talk about these here after you pause it and answer these questions for yourself. Well, if you came up with the answers as doing it the same in two-dimensional for these, you are correct. The only thing that will change is we're going to add that third component. Specifically with our dot product, remember that this is going to need to be A1, A2 plus B1, B2, and C being our K component of our third-dimensional space. And so remember, when we're finding angles in between something, it's just still going to be cosine of alpha is equal to u dot v over the magnitude of u times the magnitude of v. And that'll be the same again, just making sure you're taking into account that third parameter when finding your magnitude. And then for your unit vector here, same idea. Your unit vector is equal to your vector divided by its magnitude. All right, so let's look at a couple of these examples. Let's find the unit vector here. I'm going to go ahead and pause the film here and let you guys do this on your own, and then we'll come back together and see what you guys got together. So this is what I came up with. I found the magnitude, finding the squares of each of my parameters, and finding the sum and taking the square root. I went ahead and I didn't worry about rationalizing our denominator here, just for the sake of time. And just notice that our 3 drops down to here, our 5 drops down to here, and our -1 here drops down to there. And this is just our magnitude in our denominator, unit vector in third dimension. So here you can see this is a worked out. Notice in the book they chose to write it in the I, J, K components. Both ways will work. So if we wanted to find dot products here of these two vectors v and w, very similar to how we did it before, making sure that our i's are lined up Our J's are multiplied together, and then our K's are multiplied together, and then just find the sum of those three components, and you get the dot product of negative 2, something dot product squared. Notice similar idea as that we would get before. So now we got to talk about angle in between. The nice thing, the equation is going to stay the same. It's just going to change a little bit in our work because we are dealing with the third component. So first thing we got to do is we got to figure out, so we're going to do inverse cosine of v dot w over the magnitude of v times the magnitude of w. I'm going to go ahead and pause the video here to save some time, but go ahead and work through this and make sure you understand on how to find those values, and we'll talk about how we find the angle from there. Now that I've calculated the dot products and the magnitudes of these, I have these three parts here. Dot products negative 2, magnitude of v is square root of 14, magnitude of w is square root of 6, so I just plug and chug on my equation. So I have inverse cosine of negative 2 over square root of 14 times the square root of 6. So I'm going to pull out my calculator. Inverse cosine of negative 2 divided by the square root of 6 times 14. Close that out, and I close this out, and I get an angle of 102.6 degrees. So this is equal to theta, so I get 102.6 degrees as my theta. And just to kind of conceptualize what we're talking about, so we can think about this vector. So if this is my three-dimensional graph here, I'm going out 2 here, I'm going about 3 on my y, and I go up 1. So I'd have some vector here being my v, and then my w is going to be in the negative direction, 1, 2, and I'm going to have a j component being just a 1, and a k component being down, so I'm going to be down here. So it's kind of hard to visualize, but we are talking about this theta being the angle in between these two vectors there. So the last thing we have to talk about is we actually have 3 unique angles that we can define here as alpha, beta, and lambda, and it's how our vector interacts with each axis. So notice that alpha is the angle that interacts with my x-axis. Okay. Notice beta is the angle that interacts with the y-axis, and our lambda is the angle that it would interact with our y-axis. Okay, so we have some nice equations here. Let's really simplify the proof of these are in the book. But if we want to find this alpha, beta, and lambda, we can go ahead and use these formulas. Notice they're pretty straightforward. We'll reuse this a lot, being our magnitude, and then we just take the individual parameters and divide it by that, and then we'll use our inverse cosine to actually get those angles. So let's work through our last example here. So find the direction angles of v minus here. So the first thing I need to do is magnitude of v. So that's going to be the square root of 9 plus 4 plus 1, which is equal to the square root of 14. So cosine of alpha is equal to negative 3 over the square root of 14. Cosine of beta is equal to 2 over the square root of 14. And cosine of lambda is equal to negative 1 over the square root of 14. These just corresponding to my I and j, k components, and dividing out by my magnitude. So put in my calculator, do my inverses here. So I can do inverse cosine inverse cosine of negative 3 divided by the square root of 14. Close that out, and I get an angle of 143.3. And I'm just going to hit second enter, or second enter, and I just need to change this numerator to a 2, and I get 57.7 degrees. And then my last one, again, I don't want to retype everything, so I'm using my second enter feature. And I got to insert a negative sign, and it's negative 1 over the square root of 14. Enter, and I get an angle of 105 degrees, 0.5. All right, so that's how we find our alpha, beta, and lambda. Make sure you guys write down any questions you have and be prepared for class tomorrow. Thank you.